Hello and welcome to Science Night Tales. I am glad you have found this quiet moment to look up. Tonight, we are going to talk about a mystery that changed everything. We often think of gravity as the force that holds the universe together, pulling stars into galaxies, planets into orbits, and eventually slowing everything down. But in the late 1990s, a small team of astronomers discovered something that shouldn't be happening. The universe isn't slowing down, it is speeding up. We are going to explore the discovery of dark energy, the invisible force that is pushing the cosmos apart, and what it means for the ultimate fate of the universe. You do not need to solve the equations tonight. You can simply let the vastness of the expanding space wash over you. The stars are steady, the night is calm, and you are safe to drift. Feast. If this perspective helps you feel connected to the mysteries of the cosmos, you are welcome to like or subscribe. For now, let go of the day, and let's watch the universe expand together. Some planets never turn, not slowly, not gradually, not over hours or days. They never turn at all. One side of the planet always faces its star. The other side never does. So one hemisphere stays in permanent daylight, and the other stays in permanent darkness. No sunrise, no sunset, no shifting shadows, just endless day on one side and endless night on the other. It sounds strange. It sounds almost impossible, but it's real. Astronomers call these worlds tidally locked. They orbit their star in such a way that their rotation slows down over time. Gravity pulls on them, friction builds up inside them, their spin gradually fades, and eventually their rotation matches their orbit. One full turn for every full trip around the star. So the same face always points toward the light, and the same face always points away from it. This already happens close to home. The moon is tidally locked to Earth. We only ever see one side of it. Now imagine that, but on a planet, with a star blazing on one side forever. Some exoplanets are like this, not rare, not theoretical. They are out there right now, quietly orbiting, quietly holding the same orientation, quietly divided into two permanent halves, one side glowing, one side frozen, and between them a narrow boundary, a line that never moves, the place where day ends and night begins. It's called the Terminator line, a stable edge between light and dark. Strange, right? A world where time doesn't bring morning or evening, a world where noon never fades, a world where midnight never lifts. And yet, these planets can be stable for millions of years, sometimes for billions. No seasonal swings, no daily temperature cycles, just long-term stillness. On the day side, sunlight never stops falling. The ground stays warm. The air stays hot. The sky never dims. On the night side, sunlight never arrives. The surface stays cold. The air stays thin and heavy. The sky stays black. Two extremes, locked in place, and the planet keeps going, slowly orbiting, slowly carrying its divided face through space. This isn't science fiction. These planets have been detected around red dwarf stars, around small, cool stars that burn steadily for trillions of years. Their habitable zones are close in, so close that tidal locking becomes almost inevitable. If a planet forms there, it slows down, it locks in, and it stays that way. You might think a world like that would be broken. Too hot on one side, too cold on the other, unlivable, unstable. But something quieter happens instead. Heat doesn't just stay where it lands. Air moves, winds form, atmospheres circulate, Warm air flows from the day side toward the night side. Cool air flows back, a slow, steady exchange. Not storms in the usual sense, not violent chaos, just long-term circulation, like a planet breathing very slowly. The star keeps shining, the planet keeps orbiting, and the same face keeps looking into the light. It's a simple configuration, but it leads to a completely different kind of world. A world without mornings, without evenings, without seasons. A world that stays in one configuration for ages. And right now, there are probably thousands of them in our galaxy alone. Quietly circling their stars, quietly holding their divided form. Some of them might be rocky, some might be ocean worlds, some might be covered in clouds, some might even have atmospheres thick enough to smooth out the temperature differences. We don't know yet. We only know that tidal locking is common and that these worlds are real. It's easy to imagine rotation as something every planet must have. But gravity doesn't care about our expectations. It reshapes motion over time. It drains spin away. It pulls worlds into synchronized dances. And once a planet locks in, it stays locked, the same side, forever. So now imagine this. You're not on the surface, you're in orbit. Far above one of these planets. You're not rushing, you're not falling, you're just drifting. The star is on one side of your view, a steady disk of light. Below you, the planet curves into space, half of it bright, half of it dark. The dividing line is perfectly still, no moving shadows, no creeping night, just a fixed boundary. You move slowly along the planet's edge. On one side, the surface reflects steady light. On the other, it absorbs darkness. There is no sound here, no wind, no atmosphere brushing past you. Only silence, only slow motion, only a world holding its position in space. It feels calm, not dramatic, not violent, just steady. You keep drifting, closer now. The light side grows brighter, the dark side grows deeper, the contrast sharpens. You can see cloud bands on the day hemisphere. They don't shift much. They stay in roughly the same places, year after year, century after century. Storm systems that don't travel, they just remain. The night hemisphere is quieter, cold enough that gases can freeze out of the air. Ice can form, frost can build up. The sky above it stays black, always. And then there's the narrow zone between them, the twilight ring, where the star sits permanently at the horizon, never rising, never setting, just hovering. Low light, soft shadows, mild temperatures. This region can be stable too, not scorching, not frozen, just balanced. On some tidally locked planets, this twilight zone might be the most gentle place, the place where liquid water could exist, the place where conditions stay almost constant. No day-night cycle, no seasonal swings, just a steady environment. It's strange to think about, a world divided into three permanent regions, the blazing day side, the frozen night side, and a narrow band of calm in between. And the planet never changes its pose. It never turns its face away. It never hides one side to show the other. It just keeps showing the same halves to its star, over and over. You keep drifting closer. You're still above the boundary line. The star sits low in the sky from here, always at the same angle. The light spreads sideways, not directly overhead. The surface below looks muted. Colors don't shift with time. They stay fixed. No long shadows creeping across the ground. No golden hour. No dusk. Just the same soft illumination. And yet, this place is not dead, not necessarily. The atmosphere keeps moving, the winds keep circulating, heat keeps flowing, the planet keeps redistributing energy, slowly, gently, without drama, and all of it happens quietly, without anyone watching, for millions of years, for billions. This is the kind of world that doesn't rush. It doesn't swing between extremes. It holds them. On one side, always warm. On the other, always cold. In between, always balanced. A system locked into place. It feels almost like time itself has slowed down here. Not stopped, just stretched. You move closer still. The Terminator line is beneath you now, the exact place where light gives way to darkness. It's not a sharp edge, it's a gradual transition, a slow dimming, a soft cooling. The air changes density, the light thins, the ground temperature drops steadily, step by step. No sudden cliff, just a smooth gradient. You can imagine standing here, not burning, not freezing, just standing in a steady environment. The star would stay low in the sky forever. It wouldn't move, it wouldn't set, it wouldn't climb higher. It would just remain, hour after hour, year after year. You might lose track of time entirely. There would be no visual cue that a day had passed, only the slow passage of years marked by orbit. This is what tidal locking creates. Not chaos, not destruction, just a very different kind of stability. A stability shaped by gravity, a stability shaped by time, a stability shaped by the slow erosion of motion. And it exists. Right now, somewhere out there, planets quietly holding their divided faces to their stars. Planets with permanent day and permanent night. Planets with a narrow ring of calm between extremes. You're still drifting, not rushing, not falling, just moving slowly closer to that boundary, closer to that quiet edge, the place where light fades into darkness, the place where heat fades into cold, the place where balance quietly forms, and as you drift toward it, the world beneath you stays exactly the same. No movement, no rotation, just a steady planet, locked into its slow orbit, holding one face to the light, holding one face to the dark, and waiting quietly at the line between them. As you begin to drift closer to that boundary, toward the soft twilight zone where day meets night. The announcement in 1998 landed quietly at first. Two papers appeared almost together, one from Saul Perlmutter's group, one from Brian Schmidt's and Adam Rees's team. Together, they presented data from about 60 distant Type 1a supernovae. The conclusion was clear and startling. The expansion of the universe is accelerating. Conference rooms filled up fast after that. Whiteboards covered with plots, fluorescent lights humming overhead. Astronomers sat around long tables, scribbling notes on legal pads, passing printouts back and forth. Voices stayed low, but the questions came quickly. Is this real, or is something wrong with the data? The first doubt focused on the supernova themselves. Type 1. A explosions were trusted as standard candles, each one reaching almost exactly the same peak brightness. But what if that assumption failed at high redshift? What if distant supernova, born when the universe was younger and richer in heavy elements, behaved differently? Perhaps they were intrinsically fainter. That would make them appear dimmer without any acceleration. The teams went back to nearby supernova. They compared light curves carefully. The nearby ones looked normal. but the distant ones still came out too faint. Another possibility surfaced almost immediately. Dust. Not ordinary dust that reddens light. Grey dust, particles that absorb equally across wavelengths. If enough grey dust sat between us and those distant explosions, it could dim them uniformly. The color data would not show the usual reddening. Astronomers searched for evidence of such dust in other galaxies. They found some hints, but the amounts needed to explain the full effect seemed extreme. Still, it remained a serious alternative. The teams reanalyzed everything. They looked at multi-wavelength data, optical, infrared, ultraviolet. They adjusted for host galaxy extinction more carefully. They refined the K corrections that account for redshift stretching the spectrum. The signal stayed. The supernovae were still too faint. In one meeting, a researcher stood up and said, "We have to consider that the supernovae might be evolving." Another nodded slowly. "But the nearby sample is large. We have dozens of well-observed local events. They look the same." The discussion went late. Coffee cups collected in the center of the table. Someone sketched a new plot on the whiteboard. The curve refused to flatten. Then came the idea of inhomogeneous models. Perhaps the universe is not perfectly uniform on large scales. What if we live in a large, underdense bubble, a void? Light traveling through this region could be affected in ways that mimic acceleration. The idea had appeal. It avoided introducing new physics. It used general relativity in a different way. Teams ran simulations. They modeled light paths through inhomogeneous space. The calculations were complicated. They took time. In the end, the voids needed to be improbably large, hundreds of megaparsecs across, and even then, the effect was too weak to explain the full dimming. Another alternative appeared, varying fundamental constants. What if the fine structure constant or the gravitational constant changed slowly over cosmic time? If gravity had been weaker in the past, supernovae might have exploded differently. Or if atomic physics had shifted, the peak brightness could have varied. These ideas were intriguing. They offered ways to keep the universe decelerating. But tests from quasar spectra and atomic clocks showed no evidence for such changes. The variations, if real, were far too small. The frustration built slowly. Every alternative seemed promising at first. Then the data pushed back. Follow-up observations arrived. More distant supernovae, higher redshift events from Hubble Space Telescope. The pattern held. The curve stayed upward. In quiet moments between meetings, team members would stare at the plots on their laptops. The fluorescent lights reflected off the screens. They traced the points with their fingers. The data were consistent. The alternatives were running out of room. Yet the doubt did not vanish entirely. It lingered like a shadow. The measurements were precise, but not perfect. Small systematic errors could still hide somewhere. The teams kept checking. They kept observing. They kept debating under those fluorescent lights. A discovery this large does not arrive cleanly. It arrives in pieces. It arrives with resistance. And the more the teams looked, the more the acceleration refused to go away. But the real test was coming. The data was strong, yet still indirect. To settle the question, they needed better measurements. They needed to push the instruments harder. They needed to confront the practical difficulties of observing across billions of light years. The data held firm through those first reanalyses, but acceptance did not come easily. Every piece of evidence had to be tested again and again. The teams knew the stakes were high. One systematic error could unravel the whole claim. So they turned back to the telescopes. Nights at Cerro Tololo in Chile, long shifts at Keck on Mauna Kea. The domes opened after sunset. The temperature fell quickly. Astronomers pulled thick parkas over their shoulders, gloves on hands, breath visible in the cold dome air. They waited for clear seeing. The sky had to settle. Wind gusts rattled the structure. When conditions steadied, they began. The telescope slewed to a pre-selected field. A distant galaxy cluster filled the guide camera. They searched for the faint rise of a new supernova. These events were rare. Sometimes weeks passed without one. When one appeared, the real work started. They imaged every clear night. The light curve needed dense sampling. Rise, peak, decline. Each frame mattered. Exposure times grew longer as the object faded. Hours accumulated. The team rotated shifts. One person guided while another monitored the data stream. Fingers numb from the cold, eyes burning from staring at screens. Atmospheric distortion was constant. Turbulence blurred the image. Stars danced even through an 8-meter mirror. Seeing varied minute to minute. On excellent nights, it dropped below 1 arcsecond. On marginal nights, it spread to 2 or 3. They waited for stable pockets. They adjusted focus repeatedly. They guided manually when the auto-guiders lost lock. The joystick moved in small corrections. The crosshairs held steady on a faint guide star. Redshift measurement demanded its own patience. They needed spectra to confirm the supernova type, to measure the velocity shift. Slit spectroscopy took time. The object was faint. Exposures stretched to 1 or 2 hours per grating setting. Clouds drifted in without warning. The shutter closed. They waited again. Sometimes the night ended with only partial coverage. They scheduled follow-up for the next clear window. Weeks later, months later. Typing the supernova correctly was essential. Type 1. A explosions had specific features, silicon absorption lines, no hydrogen. But at high redshift, the spectrum stretched. Features moved into redder bands. Noise crept in. The contamination from host galaxy light complicated the picture. They took multiple epochs. They subtracted templates. They compared with low redshift samples. Disagreements arose. One team member saw clear IA signatures. Another saw possible IB contamination. They debated in the warm room after sunrise. Voices quiet, fatigue heavy in every word. Calibration ran through every observation. Flat fields corrected for pixel-to-pixel variation. Bias frames subtracted electronic offsets. Dark frames removed thermal electrons. The process happened after each night. Astronomers sat in the data room at first light. Screens filled with raw frames. They aligned images. They stacked them carefully. They measured fluxes in fixed apertures. Each small adjustment shifted the final distance by a fraction. Those fractions added up over cosmological scales. The Hubble Space Telescope entered the effort. From orbit, there was no atmosphere. Images sharper, photometry cleaner, but HST time was scarce. Proposals written years ahead, cycles oversubscribed. When time arrived, observations were tightly scheduled. The team waited for downlink. Data packets arrived in pieces. They reduced them with calibrated pipelines. 0 points matched to ground systems. Small offsets propagated into distance errors. They cross-checked obsessively. Improved CCD cameras arrived at the early 2000s. Larger formats, higher quantum efficiency, lower readout noise. The teams upgraded instruments. They tested filters again. They recalibrated 0 points. Each improvement narrowed the error bars. The acceleration signal sharpened. The curve refused to flatten, yet inconsistencies remained. Baryon acoustic oscillations provided an independent probe. Early measurements from SDSS showed clustering peaks. The acoustic scale should match predictions from CMB. But initial analyses hinted at slight offsets. The peak position appeared shifted. Was it real or another subtle systematic? The teams re-examined the power spectra. They tested different fitting ranges. They compared with mock catalogues. The tension lingered. Data points kept arriving. More supernova at higher redshift. More nights under the cold sky. More reanalyses in quiet rooms. The acceleration stayed. No single error large enough to erase it. The chill that settles into your bones after hours at the eyepiece. The faint glow of monitors in the pre-dawn dark. The quiet click of shutters opening and closing. All for a few hundred photons from explosions that happened when the universe was young. Those photons carried distance. They carried time. They forced the teams to confront something unexpected. The expansion was not slowing, it was speeding up, and the practical difficulties only made the signals stronger. But the deeper questions were waiting. If this was real, what did it mean for gravity itself? What kind of energy could behave this way? The practical difficulties only made the signals stronger. But the deeper questions were waiting. If this was real, what did it mean for gravity itself? What kind of energy could behave this way? The teams gathered in conference rooms around the world. Windows dark with evening, the air still and heavy from hours of talk. Projectors cast plots on white walls. The abstract silence of the calculations hung between sentences. They debated calmly, voices even. No one raised a tone. But the tension was there, in the pauses, in the way hands traced lines on the paper. One early alternative was modified gravity. Perhaps general relativity needed adjustment on large scales. Modified Newtonian dynamics had been around since the 1980s. It was designed to explain galaxy rotation curves without dark matter. Now, some suggested it could explain acceleration too. In MOND, gravity weakens more slowly at low accelerations. The threshold is tiny, about 10 to the power of -10 meters per second squared. Below that, the law changes. Simulations ran on early computers. They showed flat rotation curves. They showed promise for the cosmic scale. But then the tests came. Solar system constraints were tight. Planetary orbits followed general relativity precisely. MOND struggled there. It needed tweaks to fit Cassini probe data. The acceleration threshold was too low to affect planets. But on cosmic scales, it worked better. The debates went on. One astronomer said, "It fits the supernovae without new energy." Another shook their head. "The CMB peaks don't match." They ran more simulations. The code hummed through the night in quiet server rooms. Results came back. MOND could mimic acceleration in some models. But the baryon acoustic oscillation scale shifted slightly. It did not align with observations. the tension grew. F of R gravity offered another path. This modified the Einstein-Hilbert action. The Ricci scalar R gets replaced by a function f of R. In some forms, it produces self-accelerating expansion. No need for dark energy. The field equations change. On small scales, it reduces to general relativity. On large scales, it deviates. Teams coded numerical solvers. They evolved the universe from the Big Bang. The growth rate of structure slowed. It looked like acceleration, but again, the tests. Solar system again. The parameterized post-Newtonian parameters had to match. F of R models were tuned. Some passed local tests, others failed galaxy cluster dynamics. The debates intensified. In one session, a theorist drew the F of R form on the board. This term drives the late acceleration. A cosmologist replied, "But look at the void profiles. They don't match SDSS data." Quintessence emerged as a different option. This was a scalar field. It rolled slowly down a potential. Its energy density decreases over time, but slower than matter or radiation. The equation of state W is between -1 and -1/3. It can vary. Simulations incorporated the field. They tracked its evolution. Early on, it behaves like radiation. Later, like a cosmological constant. It fits the supernovae. It fits the CMB. The appeal was clear. Quintessence is dynamic. It could explain why acceleration started recently. The coincidence problem, why now, found a natural answer. Teams explored potentials, exponential, inverse power law. They ran Markov chain Monte Carlo fits. The constraints from data tightened. W close to -1, but deviations allowed. Phantom energy took it further. W less than -1. The field climbs up the potential. Energy density increases with time. Expansion accelerates faster and faster. Eventually, a big rip. Everything tears apart. Galaxies, stars, atoms. The simulations showed it. Scale factor diverges in finite time, but observations constrained W. It could not be too negative. Solar system tests again. Phantom models struggled with stability. LCDM, the lambda cold dark matter model, stood as the benchmark. Lambda is the cosmological constant. W equals -1 exactly. It fits everything. Supernovae, CMB, BAO. But why lambda? Why that value? The debates circled back. Alternatives avoided vacuum energy problems, but they introduced new parameters, more tuning. Failed tests piled up. MOND clashed with cluster lensing. F of R predicted wrong galaxy growth rates. Quintessence needed fine-tuned initial conditions. Phantom risked instabilities. Each simulation run, hours on clusters, returned mismatches. The abstract silence after bad results. Teams stared at error bars. The data favored LCDM, but not decisively yet. The tension thickened. Every model had strengths. Every model had flaws. The acceleration refused easy explanation. The calm tones hiding frustration. The simulations running through the night. The step-by-step breakdowns leading nowhere certain. Yet the evidence was shifting. New data streams were coming. They would tease acceptance. The alternatives grew more sophisticated, but the evidence was shifting. New data streams were arriving. They would tease acceptance. In the early 2000s, the teams kept watching. More supernovae, more redshifts. The curve on the Hubble diagram held its upward bend. But supernovae alone were not enough. They needed independent confirmation. Something that measured the same expansion history from a different angle. The cosmic microwave background offered that angle. The radiation left over from the Big Bang, it fills the universe uniformly. Tiny temperature fluctuations in the CMB carry the imprint of early density variations. Those variations grew into the galaxies we see today. The power spectrum, the pattern of hot and cold spots, reveals the geometry of space. WMAP launched in 2001. It mapped the sky in microwave bands. The first results came in 2003. The power spectrum showed clear acoustic peaks. The first peak position told us the angular diameter distance to the last scattering surface. In a flat universe, that distance corresponds to a specific angle. The peak lined up perfectly with flatness. Omega total near 1, but matter, ordinary plus dark, only accounted for about 30%. The rest had to be something else, something with negative pressure. Dark energy fit exactly. The room where the WMAP team presented those plots was quiet. Screens glowed with the spectrum, the first peak sharp and clear. Astronomers leaned forward. One said softly, "That's flat." Another nodded, and the amplitude matches LCDM. Planck followed in 2009. Higher resolution, better frequency coverage, more precise foreground subtraction. The 2013 release sharpened the picture. Omega matter at 31%, Omega lambda at 69%. The equation of state W consistent with -1. The data converged. Large-scale structure surveys added another layer. The Sloan Digital Sky Survey, SDSS, mapped millions of galaxies. It measured baryon acoustic oscillations. The sound waves from the early universe left a characteristic scale, about 450,000 light-years at recombination. That scale stretches with expansion. In the galaxy distribution today, it appears as a peak in the correlation function. The position of that peak measures the angular diameter distance and Hubble parameter at different redshifts. SDSS data from the mid-2000s showed the acoustic peak clearly. The scale matched predictions for a dark energy-dominated universe. Growth rate measurements came next, the way structures clump together over time. In a decelerating universe, growth is faster. In an accelerating one, it slows. SDSS measured the growth function. It was lower than matter-only models predicted. Dark energy suppressed clustering. The tension eased. In data rooms, the teams gathered. Humming computers lined the walls. Screens showed power spectra, correlation functions, error ellipses shrinking with each new release. Someone pointed at a plot. "Look, the growth curve drops exactly where it should." Another traced the contour. W is pinned at -1. The gradual confirmations settled in. WMAP, SDSS, more supernovae from Hubble. Each dataset independent, each pointing to the same conclusion. The universe is flat, matter is minority. A smooth, constant energy density dominates, dark energy. But gaps remained. The equation of state W had error bars. It could deviate from -1. If W was slightly different, the future would change. Quintessence would return, phantom energy possible. The teams kept fitting. They ran MCMC chains overnight. Results came back. W consistent with -1, but not perfectly. The tension lingered in small corners. In one session, a cosmologist stood at the whiteboard. He drew the current constraints. Omega lambda dominating. W close to -1. He said quietly, "We're converging." Someone else added, "But we're not done." Feel the slow turn of that moment, the hum of servers in the background, the soft glow of plots on the wall. Years of nights at telescopes, years of reanalyses, years of doubt, all leading to this quiet agreement. Dark energy was no longer just a possibility. It was the simplest explanation. It fit the data, it dominated the energy budget, and it was driving the universe toward a future very different from what anyone had expected before 1998. The pieces were falling into place, the evidence was converging, but the full picture, its implications, its nature, its consequences, was only beginning to. The tension thickened for years. Every alternative was tested, every model pushed to its limit, and slowly, quietly, the evidence began to converge. In the mid-2000s, the pieces started fitting together, not in one dramatic moment, but in a series of careful steps. Each new dataset arrived like a calm wave. It washed over the doubts. It left the shape clearer behind. The supernova data had been the first signal, distant explosions fainter than expected, the curve bending upward. But supernova alone carried uncertainties. They needed anchors. They needed cross-checks from completely different physics. The cosmic microwave background provided one. WMAP had shown flatness in 2003. Planck sharpened it in 2013. The power spectrum, those peaks and troughs, measured the angular size of the acoustic horizon. In a flat universe, the first peak sits at a precise angle. It did. Omega total was 1. Matter, baryonic and dark, accounted for 31%. The rest had to be something with negative pressure, something that did not dilute as space expanded. Dark energy fit, and the fit was tight. Teams gathered in analysis rooms. Screens showed the angular power spectrum. The second peak, the third, the damping tail, all aligned with a cosmological constant. One cosmologist pointed at the plot. "See how the third peak sits exactly where lambda predicts." Another nodded slowly. "No room for modified gravity here." Baryon acoustic oscillations gave the next confirmation. SDSS had mapped hundreds of thousands of galaxies. The correlation function showed a clear peak. The acoustic scale, stretched by expansion, acted as a standard ruler. Measure its angular size at different redshifts. You trace the distance history. The BAO peak position matched the supernova curve. It matched the CMB. The growth rate of structure, how clusters form, slowed as expected in an accelerating universe. Dark energy suppressed clustering. The data agreed. In one session, the team projected the combined constraints. Contours on the W-omega plane, the supernova ellipse, the CMB ellipse, the BAO ellipse. They overlapped in a small region. W close to -1, omega lambda near 70%. The room was quiet, the hum of projectors. Someone said softly, "We're pinned." Multi-wavelength observations closed the dust loophole. Ordinary dust reddens light. Grey dust would not. The teams observed supernovae in optical, near-infrared, and ultraviolet bands. They measured colors carefully. If grey dust were responsible, the dimming would be wavelength independent. But the reddening was consistent with normal dust. The extra dimming remained. Dust could not explain the full effect. The acceleration signal survived. The equation of state W came into focus. Supernovae alone allowed W between -1.2 and -0.8. CMB tightened it. BAO tightened it more. The combined constraint centered on -1, with errors small enough to rule out many quintessence models. Phantom energy, W less than -1, was disfavored. It risked instabilities. The cosmological constant looked cleaner, simpler. In data rooms, the teams ran joint likelihoods. Chains sampled parameter space overnight. Plots appeared at morning meetings. Error ellipses shrank. You hovered at -1.02 plus or -0.05. Still room for dynamics. But the center was clear. Decades of work, nights at telescopes, reanalysis in quiet offices, simulations running through weekends, all converging on one conclusion. The universe is accelerating. Dark energy dominates. Its density stays constant. Its pressure is negative. W is -1. The tensions that once kept everyone awake began to ease. Dust ruled out. Evolution bias constrained. Modified gravity pushed to the edges. The data spoke clearly. Dark energy was not an artifact. It was real, and it was the largest component of the cosmos. With that acceptance came a new view. The proofs we had gathered, supernovae, CMB, BAO, were solid. They measured the expansion history. They measured geometry. They measured growth, all consistent. But they also opened the door to larger questions. If dark energy drives acceleration, what does it mean for the structure of the universe? How does it shape galaxies and clusters? How does it write the long-term fate? Those answers were emerging, and they carried a deeper humility. The confirmations were undeniable. Supernovae, CMB, BAO, all converging on dark energy as the driver. The equation of state pinned near -1. The tensions from dust and calibration faded. We could finally look beyond the data points. We could see how this force reshapes the universe on its largest scales. Dark energy does not cluster like matter. It spreads evenly through space. Its density remains constant as the universe grows. That constancy changes everything. In the early universe, matter dominated. Gravity pulled things together. Density fluctuations grew. They formed filaments and voids. The cosmic web took shape. But as expansion continued, dark energy's influence rose. It suppresses structure growth. Gravity tries to clump matter. Dark energy stretches space faster. The pull weakens over time. Simulations show this clearly. Run on massive computers, they evolve the universe from the CMB era forward. Initial seeds from inflation. Matter collapses into halos. Galaxies form along filaments. But with dark energy, the growth rate slows after redshift 1. Clusters stop merging as frequently. The web freezes in place. Reference those simulations for a moment. Screens filled with evolving grids. Points representing galaxies drifting apart. Voids expanding like quiet breaths. Filaments thinning. The vast expansions play out over billions of years in minutes of compute time. Teams watch the runs complete. They adjust parameters. Without dark energy, structures keep growing. Too many massive clusters. With it, the numbers match what we see. The future freeze-out becomes clear. In 10 billion years, expansion doubles the current rate. Galaxy groups like our local group stay bound, but beyond 50 megaparsecs, everything recedes faster than light can cross. The observable universe shrinks. Distant galaxies redshift beyond detection. The cosmic horizon closes in. Detail that process slowly. First, the most distant clusters vanish. Their light stretches to infinite wavelength. Then nearer ones follow. Our sky empties. The Milky Way-Andromeda merger completes. The new galaxy sits alone in a vast void. Stars burn out. Black holes evaporate. Protons decay if they do. The freeze-out leaves a cold, sparse expanse. Link this to possible origins. Dark energy might be quantum vacuum energy. Zero-point fluctuations in empty space. Fields vibrating at Planck scales. The cosmological constant lambda. Calculations predict its value, but the predicted density is 120 orders too large, the worst mismatch in physics. Teams explore why. Fine-tuning? Multiverse? The questions linger. New fields offer another view. Quintessence, a scalar field rolling down a potential. Its energy density decreases slowly. W slightly above -1. It could vary over time. Simulations test this. Early quintessence behaves like dark matter. Later, it dominates. The growth suppression shifts slightly. Current data allows small deviations, but Planck and Deci tighten the bounds. W equals -1.03 plus or -0.03. Edge limits appear here. If W dips below -1, phantom energy. Expansion accelerates without bound. A big rip in finite time. Atoms tear apart, horizons dissolve, but data disfavor it. W greater than -1.1. The universe stays intact, just increasingly empty. Dark energy is not just a number in equations. It sculpts the cosmic web. It sets the pace of expansion. It shapes voids that span hundreds of megaparsecs, filaments that thread galaxies like quiet rivers. The vast expansions we observe, clusters receding at thousands of kilometers per second, are its work. Humility follows. We measure this force from mountaintops and satellites. We simulate its effects in quiet rooms, yet its nature eludes us. Vacuum energy, a new field, something else. The answers touch the edges of physics. Quantum gravity, the Planck scale, where our theories meet their limits. Those edges call us forward. The fate dark energy writes is not just distant, it is profound. It redefines our place in time. The revelations settled slowly. Dark energy was real. It dominated. It shaped the web of galaxies and voids. It suppressed growth. And now we could see where it leads. The fate of everything. In 10 billion years, the expansion doubles again. The rate keeps rising. Distant galaxies recede faster than light can bridge the gap. Their light stretches redder and redder. Wavelengths grow longer. Eventually, they vanish. Not because they stop shining, but because their photons never reach us. The cosmic horizon closes. Our local group, Milky Way, Andromeda, a few dozen dwarfs, stays bound. Gravity holds it together. The merger of Milky Way and Andromeda finishes. A single elliptical galaxy forms. Stars orbit in wide arcs. But beyond that group, the universe empties. Cluster after cluster crosses the horizon. The sky darkens. Fewer galaxies visible. Fewer stars. The last light from distant sources fades. Pause here. Imagine that night sky, once filled with galaxies. Now only the faint glow of our own merged system. A single island in expanding darkness. Stars continue burning. Hydrogen fuses into helium. Helium into heavier elements. In trillions of years, the last low-mass stars die. White dwarfs cool. Brown dwarfs drift. Black holes remain. They accrete stray gas. Slowly, very slowly. Hawking radiation begins to matter. Even the largest black holes evaporate. Stellar mass ones take 10 to the power of 67 years. Supermassive ones take 10 to the power of 100 years. The temperature rises as they shrink. Final stages produce a burst, gamma rays, particles, then silence. If protons decay, as some theories predict, the decay timescale is around 10 to the power of 34 years. Atoms break apart, matter dissolves. The universe becomes a sea of leptons and photons. Entropy maximizes. Temperature approaches absolute zero. No gradients, no work, heat death. The cosmic microwave background cools from 2.7 Kelvin today to micro-Kelvin to pico-Kelvin. Photons redshift forever. Wavelengths stretch to the size of galaxies, then larger. The background becomes undetectable. Speculations fill the edges. If W is exactly -1, eternal expansion. No rip, no crunch, just dilution. If W deviates slightly above -1, quintessence decays. Expansion slows, but current bounds keep it near -1. If below, phantom energy. Big rip, but data disfavor it. W greater than -1.1. The universe stays, just emptier. Tie this to reality's structure. Dark energy ties directly to the vacuum. Quantum fluctuations, zero-point energy, the cosmological constant. It curves space on the largest scales. It determines the geometry. Flat, open forever. The fate is written in that curvature. In the way space responds to this constant energy density. The desolation feels vast, not violent, not sudden, just inevitable. Galaxies once close enough to see become unreachable. Light that left them billions of years ago never arrives. The observable universe shrinks to our local group, then to our galaxy, then to nothing but faint remnants. Reflective tone settles here. We discovered this future from mountaintops, from satellites, from quiet data rooms. We measured the force. We simulated its path. We know the outline of the end. Yet humility follows. Our moment is brief, a flicker in cosmic time. We observe the early chapters. The stars still shine, galaxies still cluster, but the long arc points toward silence, toward isolation, toward a universe that cools and spreads until nothing moves. This fate is not punishment, it is physics. Dark energy does what it does. Constant density, negative pressure, expansion without end. The story we have followed, from the first faint supernova to this distant horizon, carries us to acceptance. Not despair, acceptance. Wonder at the scale, humility at our place within it. And that acceptance opens the final reflection. What does it mean to know this? To stand on a small planet, to look at the night sky and understand the quiet path ahead. The revelations brought us to the edge. Dark energy shapes the present. It suppresses growth. It expands voids. But what of the far future? What roles does it play when matter fades and time stretches long? Let us look ahead slowly. In a universe with W exactly -1, expansion continues eternally. No end, no collapse, no rip. The scale factor grows exponentially. Distances double every 10 billion years or so. Today, then faster. Distant galaxies cross the event horizon. Their light never reaches us. The local group holds together. Gravity binds it. Milky Way and Andromeda merge. Triangulum stays close. A few dozen dwarfs orbit. But beyond that boundary, the cosmos empties. Virgo cluster recedes. Coma cluster follows. One by one.
To listen
The observable universe shrinks to a bubble 50 megaparsecs across, then smaller. The sky darkens. Teams today model this in simulations. They run codes on clusters, initial conditions from Planck data. The grid expands, galaxies drift apart. The web thins, voids grow vast. Filaments snap. The expansions unfold gradually, step by step, each time step a million years. The runs take days. Results appear on screens in quiet labs. Astronomers watch the fade. Stars die out. The last red dwarfs burn their fuel after trillions of years. White dwarfs cool to black. Neutron stars spin down. Black holes dominate for eons. They accrete stray atoms. Hawking radiation nibbles at their mass. Slowly at first, the horizons shrink. Temperatures rise. Final bursts release energy. Then nothing. If protons decay, matter dissolves. Timescale around 10 to the power of 34 years. Nuclei break. Electrons and positrons annihilate. Photons and neutrinos remain. The universe becomes a dilute gas. Temperature drops from microkelvin to attokelvin. No gradients, no work possible. Entropy at maximum. Heat death. Big rip alternatives arise if W dips below -1. Phantom energy. Density increases with expansion. The scale factor diverges in finite time. First galaxies tear apart, then solar systems, planets, atoms. The rip happens in 10 to the power of 11 years or so. But data constrain W above -1.1 at 95% confidence. Phantom models are disfavored. The eternal expansion holds. Gradual expansions on isolation deepen the picture. In 100 billion years, all galaxies outside the local group are beyond the horizon. Their light frozen in time. We see them as they were billions of years ago. But no new light arrives. The sky is static, a snapshot of the past. Reference the teams exploring this, cosmologists in modern observatories. They input current parameters, lambda at 69%, W at -1. The codes evolve forward. They pause at key epochs, 100 billion years, 1 trillion years, 10 to the power of 100 years. The displays show isolation growing, fading light, diminishing structure. The calm tone of these projections settles in. No catastrophe, just steady dilution. Dark energy's role is simple. Constant pressure, endless push. It outlasts matter. It outlasts radiation. The universe becomes de Sitter space. Empty. I-curved only by lambda. Build the reflective tone. We measure this from our brief era, from mountaintops and satellites. We simulate the end, yet we will never see it. Our galaxy merges long before the isolation completes. Humanity, if it persists, watches the sky empty slowly. Wonder at the scale, melancholy in the inevitability. The expansions continue, horizons fade, light dims. This long view invites us back to reflect on the journey from the first faint supernova to this quiet cosmic end. The speculative futures we have looked upon, the endless expansion, the fading horizons, the slow cooling toward heat death, carry us gently to the end of this journey. What began with faint light from distant explosions has brought us here, to a quiet acceptance, to a place where the scale of it all settles in the chest like a slow breath. Let us walk back through the path we have taken. It started on mountaintop nights, cold air, clear skies, astronomers in control rooms watching for supernovae. The High Z team, the Supernova Cosmology Project. They collected light curves, measured redshifts, plotted distances. the points refused to follow the expected curve. The universe was not slowing, it was accelerating. Doubt came quickly. Conference rooms under fluorescent lights, whiteboards filled with alternatives, grey dust, evolving supernovae, inhomogeneous models, modified gravity, quintessence, phantom energy. Each idea tested, each one pushed back by data. The teams reanalyzed. They observed more. They waited through long nights for photons that had traveled billions of years. The practical struggles deepened the story. Atmospheric distortion blurring images, redshifts hard to measure in faint spectra. Typing supernovae correctly when features stretched into noise. Calibration sessions at dawn. Improved CCDs arriving. Hubble space. Telescope time granted after years of proposals. Every refinement narrowed the error bars. The acceleration signal sharpened. Then the independent confirmations arrived. WMAP and Planck mapping the CMB. The power spectrum peaks aligning with flatness. Omega total near 1. Matter only 31%. Dark energy the rest. SDSS and other surveys tracing baryon acoustic oscillations. The standard ruler stretching as expected. Growth rates slowing exactly where acceleration predicts. The contours overlapped. W close to -1. The pieces fit. Dark energy emerged as the simplest explanation. A constant energy density. Negative pressure dominating 68% of the cosmos. It suppresses structure growth. It expands voids. It thins filaments. It shapes the cosmic web we see today. And it writes the long future. Galaxies beyond the local group recede beyond the horizon. Their light freezes in time. The sky empties. Stars burn out after trillions of years. Black holes evaporate across 10 to the power of 100 years. The microwave background cools to nothing. Heat death arrives, not with violence, with silence. Pause here. Let the night sky come into focus. Look up. The same sky those astronomers watched decades ago. Stars still sharp, galaxies still visible, the light from distant supernovae still arriving. But now we know. We know the path ahead. We know the force behind it. This knowledge brings humility. We are small, a brief flicker on a small planet. Yet from here, we measured something that controls the fate of everything. We traced the expansion history. We constrained the equation of state. We simulated the future. We asked questions that outlast us. The wonder lingers. Not because the universe is kind, not because it promises eternity, because we can understand even a fraction of it, because we can stand under the stars and see the long arc, from the Big Bang to heat death, from doubt to acceptance, from a handful of faint explosions to the quiet end of everything. The story does not close with answers. It closes with questions that remain open. What is dark energy exactly? Vacuum energy? A field? Something deeper? We continue to watch. We continue to measure. We continue to wonder. Rest now with the night sky above you. The wind moves gently. The dome of stars turns slowly. The universe expands, and we are here. Briefly, aware, curious. May that curiosity stay with you. Long after the words fade, long after the light from those distant supernovae reaches us. The journey is not over. It continues in every clear night, in every question we still ask. Thank you for walking this path together. The sky waits,